So in chapter 6, we are going to be solving a new type of maximization problem. So in the previous sections when we used matrices to solve some of these problems, we made assumptions, or we assumed that we had to use all of some material. And as we saw in the example when we were moving cars, making that assumption may not give us the optimal solution. So we're going to spend some time in chapter 6 doing what's called linear programming or general linear programming, which is a way for us to maximize and minimize things. So oftentimes these things are phrased in terms of inequalities instead of equations, because inequalities just give us boundaries of things that have to be true. Like you only have so much money to spend, or you only have so much of this material, but an inequality doesn't force us to use all of that. So it may not be beneficial to spend all of your money. Maybe the optimal solution is somewhere less than that. And so we're going to take what we've seen of inequalities and we're going to expand them into more dimensions. So let's just take a second and remind ourselves a little bit about one variable inequalities as we get started. All right, so to solve an inequality is to find the set of all values that make the inequality true. The solution to x is less than 6 is the half line, or the interval, negative infinity to 6. The solution x less than or equal to 6 is also a half line, but the interval would be negative infinity to 6 included. In both cases, there are infinitely many x that make this inequality true. So to solve, for example, the inequality that we have here, we would solve it the same way we do a linear equation, which is we would get x by itself. So we would add 7 to both sides, and that gives us 3x is less than negative 7. We divide by 3 and divide by 3, and that gives us x is less than or equal to negative 7/3. So in terms of a solution, it would be from negative infinity to negative 7/3, including negative 7/3. And we'd solved problems like this in the past by putting them on a number line. So 2, 3, so negative 7/3 would be right there. And then we would shade the region that we would want, so everything less than negative 7/3, right? Okay, so the one thing we do have to remember, and the only difference between solving an equation and an inequality is, when we have an inequality, if we multiply or divide by a negative number, what do we have to do? You have to remember to reverse the inequality symbol. So that's really the only thing that's going to be different in any of these. All right, so now we've done one-dimensional inequalities for forever. Now we want to start expanding to multiple dimensional inequalities, because in real life, we're going to have to solve problems in business that involve more than one variable. So before we jump to a ton of variables, the or more part, let's start with an inequality involving 2 variables, because a lot of what happens in 2 dimensions generalizes well to higher dimensions. So an inequality in 2 or more variables can be written in the form where all of our variables and their coefficients are on the left-hand side, and then we have a less than or equal to, a less than, a greater than, or a greater than or equal to some number on the right. And if we have more than 2 variables, sometimes we'll use x, y, and z. Sometimes they will just subscript all of the variables to represent what they are. But we'll notice that in both of these cases, we are dealing with only linear equations. So we have no interaction terms, right? So there's no x1 times x2, no x times y, no anything like that. They are all linear in one variable. All right, so we want to solve the inequality 2x plus 3y is less than 6. So we can then graph the corresponding line. So if we were to graph (2x plus 3y is equal to 6), we could graph this by the intercept method. If we pick x is equal to 0, we would have 2 times 0 plus 3 times y equals 6. Well, anything times 0 is 0, so we divide by 3, and we would get y is the same as 2. So that gives us the point 2, 0. And then we would find the other intercept by setting y equal to 0. And that would give us 2x plus 3 times 0 equals 6. Once again, anything times 0 is 0. So we divide by 2, and this time we get x is equal to 3. So I wrote my first ordered pair backwards. X was 0, y is 2. Here, x is 3, and y is 0. So if we plot our points, we have 0, 2, and the point 3, 0. And we have an or equal to, so we're going to draw a solid line. So we've got this, but we have an inequality. We want 2x plus 3y to be less than or equal to 6. So similar to what we did up here, we need to shade a half plane. But we don't know which one to shade. So we're going to pick a sample point to help us determine which side to shade. So let's pick a sample point. To determine which half plane to shade. So the easiest one to pick if it's available is 0, 0, because anything times 0 is 0. So let's pick the point 0, 0. And if we plug that into our original equation, we have 2 times 0 plus 3 times 0. And we want to know, is that lesser than or equal to the number 6? Well, 0 plus 0 is going to be 0. So we get 0 is less than 6, and that is true. So we picked our sample point here, and it's true. So then it tells us that that is the side of the line that we need to shade. So then our solution is this half plane, or everything below that line. So just to be explicit, what if I picked this point right here? What would its ordered pair be? 1 and 4, right? If I check this in the inequality, 2 times 1 plus 3 times 4, is that less than or equal to 6? Well, that's 2 plus 12, which is 14, which is not less than or equal to 6, right? So we were just picking one point to check, because we know on the line is where 2x plus 3y is 6. But now we need to determine, well, which half was really the solution. So you pick a point on either side, and as mentioned, 0, 0 is always a good choice because it's the easiest one to check if it's available. If the line goes through 0, 0, you will have to pick something else, like what we did here. And if it's false, then it's the other side that you need to shade, right? So this is really just the two-dimensional analogy of what we did up here. But up here with one-dimensional inequalities, we never had to pick sample points. But we could to check, but we didn't need to. In 2 dimensions, it is going to be required. And as we find out, in 3 or more dimensions, things get a little dicey. And we'll come up with some other methods for how that is going to work. All right. So let's take a look at our next picture. So what if we had more than one inequality? So in the past couple of chapters, we solved systems of linear equations. And when we solved a system of linear equations, we found a point, right? It was the intersection of those two curves. Well, if we graph this system of linear inequalities, which is done here, so just to emphasize, this is the red line, and it's dashed because it's not included. This is the blue line, and it's dashed because it's not included. This point right here is the solution to the system of equations x minus y equals 0, and x plus 3y equals negative 12. But we don't have a system of equations, right? We have a system of inequalities. So when we solved an inequality up here, what happened? We got a half plane. So in this one, the solution to 2x plus 3y is less than 6 was this whole red chunk below the line. Well, up here, we get something similar, and I've graphed each of them, so red and blue. So the red solution was everything below the line, so everything down here, and the blue one was everything up here. But we need both of these inequalities to be true. So when you mix red and blue, what do you get? Purple, right? So we see this region right here that we have is the solution. So this is both red and blue. So this is the and, or the intersection of those two sets. So the solution would be everything that's in that purple region. So if I were to pick a point, say this point out here, which inequality would that satisfy? So if I picked the point negative 2, 4, out of these two inequalities, which one would it make true? The red one or the blue one? Well, is it in the red shaded region?
Would it be the blue one because it's in the blue area?
Yeah, exactly. It's in the blue region, so it would make the blue inequality true. It's not in the red region, so it wouldn't make the red one true. And if we checked it, we would have negative 2 minus 4, and we want to know, is that bigger than 0? Well, or not minus a minus 4, minus 4. And if we do that subtraction, negative 2 take away 4 gives us negative 6, which is not bigger than 0, right? But if we check it in the blue inequality, negative 2 plus 3 times 4, is that bigger than negative 12? Well, negative 2 plus 12 is negative 10, which is bigger than negative 12, right? Similarly, if we checked a point down here, it would make the red one true, but not the blue one. But here, if I pick this point, say 3, 0, since it's in the purple part, which is both red and blue, it would make both of them true. So the idea when we have a system of inequalities is we need to find the region where the two inequalities overlap. So this raises a couple of questions. If I graph two half planes, will they always intersect? Will there always be a solution? So what do we think? So if we add x is less than 0 to that picture, so if I were to grab orange and graph x equals 0 is this vertical line, and I want everything that's less than it, that would be over here, right? So then it would be where the purple and the orange overlap, which is going to be here. So one thing we're going to notice when I start shading all of these multiple colors and all of these multiple regions, these graphs get really, really hard to read very, very fast. So instead of using the convention that we've been accustomed to in algebra to shade what we want, we're actually going to do the opposite. So if we come down here, in our textbook, what we would do is we would eliminate or shade what we don't want. So let's imagine now shading the regions we don't want as we do this. So the regions we didn't want for the red line was everything above the line, right? So it would say we would shade what we don't want. So essentially we get rid of everything up here. For the blue region, we wanted everything above the blue line. So we shade what we don't want, which was everything below the blue line. And then now we add our last line, which was x equals 0, and we shade what we don't want, which is this over here. So when we get rid of what we don't want, the picture then, what left is the solution we are looking for. So I know that goes against the way that we've normally been taught inequalities, but as we add more and more things to this, you'd have to have like 50 colors and it gets super busy. So it's easier to just eliminate what we don't want. So then everything that's left is what we do. So then the solution to all of them would just be that region here contained by those three lines. So this little triangular region would be our solution. All right. So let's go ahead and resolve example number 3. So we want to graph each of these and find the corresponding solution sets. So we have 5x minus 2y is less than or equal to negative 4. 2x plus 5y is less than or equal to 10. And 3x minus 7y is greater than or equal to 15. All right.
Professor, I have a quick question.
Yes, ma'am. Resolve our first one. So if we take our first inequality right here, so we have 5x minus 2y is less than or equal to negative 4. So we need to draw a graph of this. So there are several different ways that we can do so. So one method is to just get y by itself. So we minus 5x, we minus 5x. That gives us negative 2y is less than or equal to negative 5x take away 4. And then we divide by negative 2, divide by negative 2, and divide by negative 2. So we get y, but since we divided by a negative, we have to reverse our inequality symbol. 5 over 2x, and negative 4 divided by negative 2 is plus 2. So if we graph this, it is now a line. We have our y-intercept is 2, so that's going to be this point. So 0, 2, and then our slope is 5 over 2. So I go up 5 over 2. Or down 5 and left 2. So down 1, 2, 3, 4, 5, and left 2. And we play connect the dots. And then if we do a checkpoint, we can check 0, 0. If I plug 0 in, is 0 bigger than 0 plus 2? No. So 0 is not bigger than 0 plus 2. So this is false. So we want to that 0, 0 is not in the solution set. So then if this is not in the solution set, that's going to be the side that we block off, right? I'm going to wait to block it off for a second because it makes it hard to graph things. So let's take a look at our next set. So we have 2x plus 5y is less than or equal to 10. So we can do the same thing again. This time we can use the intercept method pretty easily, or the y-intercept method and x-intercept, because 2 divides into 10 and 5 divides into 10. If we go up to our previous one, the reason that wouldn't work out so well is 5 does not divide into 4 evenly. So if we pick x equals 0, that gives us 5y equals 10. We divide by 5, we get y is 2. So we get the ordered pair 0, 2. And if we pick y equal to 0, that gives us 2x equals 10. Divide by 2, we get x is 5. So that gives us 5, 0. So we have our point 5, 0, and we have our point 0, 2, which is right here. And we get something that looks like this. And we'll do our test points in a second. Let's get our third one. So in green, our last one is 3x minus 7y is greater than or equal to 15. So in this case, it's not going to be pretty because none of our things divide. So let's just set up the equation and see if we can find some values that will work out well. So one of them that will work well is if we pick y equals to 0, then we get 3x is equal to 15, gives us divide by 3, we get x is 5. And that's good because we get the point 5, 0. But if we pick x equals 0, we're going to end up with a fraction, which isn't going to be helpful. So if we picked x equals 0, we get negative 7y equals to 15, right? And 7 doesn't divide into 15. And I can't really graph negative 2 1/7 by hand. So we're going to want to pick a different value for x. So let's see. What if we pick x to be negative 2? If I do that, I get 3 times negative 2 minus 7y equals 15. So that's negative 6 minus 7y equals 15. I add 6 and I add 6, and that gives me negative 7y equals 21, which divides, negative 7 divides into evenly. We get y equals to negative 3. So that gives us the point negative 2, negative 3. And you might be saying, well, why did you pick negative 2? The answer to that question is because it works. And you might be saying, well, that's a terrible explanation. And I agree with you. So let's talk a little bit about the reasoning I did in my head. So I know if I picked x equals 0 that 7 didn't go into 15, right? So I needed to move something over to the other side, namely this term. So if I subtracted this over, it would be 3x, right? Well, what are the numbers that are divisible by 7? 7, 14, 21, 28, 35, and so forth. So basically, I picked an x that gave me one of those numbers. So if I picked x to be negative 2, that would make me add 6, and 15 plus 6 is 21, right? So that's the reasoning that I went through to help me pick that point. So now we have 5, 0, and -2 and 3. So we get something that looks like this. All right, so now let's find our feasible region for this solution. So we start down here with our green equation. Let's check. So if I check 0, 0, is 0 minus 0 greater than or equal to 15? So that tells me, well, is 0 minus 0 bigger than 15? Is 0 bigger than 15? No. So then that says that 0, 0 is not in the solution. So what would I need to do? I shade what I don't want. So that means everything above the green line is gone. Right? So then I go to the blue line, which is just going to be this region over here because it's the only thing that's left. If I check, I can't check 0, 0 anymore because we don't really care. Well, I guess we could, but it's not going to matter. So if we put 0, 0 in, 0 plus 0, is that less than 10? Sure, so the region below the blue line is what we want, so we would shade out here. Well, that's already gone. And then we check 0, 0 in this one, which we already did, which means we don't want 0, 0. So that means we would get rid of everything below 0, 0. So that's going to be this part. So now we're left with all of this being gone. So the region that's left is actually just this teeny part right down here that goes on forever, right? So we get this teeny part down here. Well, it's not actually teeny because it's going to be infinite because those two lines go forever, right? And that's going to be our solution to that inequality. So that gives rise to our next definition that we're going to see right here. Bounded and unbounded solution sets.
Professor?
Yes, ma'am.
So you're saying that one of
Gives rise to our next definition, which is we want to talk about bounded and unbounded solution sets. So the solution set in example 3 is unbounded. A set is unbounded if it is not possible to draw a rectangle that contains the set. So it's unbounded because if I came up here, if I tried to draw a rectangle that contained this set, I could draw two things like here, but the problem is since it goes down forever, I could never finish drawing a rectangle that would contain that set because it goes down to negative infinity and it also goes left to negative infinity, right? So it would be impossible for me to draw a rectangle that contains that entire set. If we go back to this example, this is an example of a bounded set because could I draw a rectangle that contains that entire set? Certainly, right? So that region there is contained within this rectangle. So this set is bounded. But the example we just did is unbounded because I cannot draw a rectangle that contains the solution. So when we're doing linear programming problems, our methods are going to have to change whether sets are bounded or unbounded. So our definition for an unbounded set is if it is not possible to draw a rectangle that contains the set. A set is bounded if there exists a finite rectangle that contains the solution. So one thing to note, depending on which math books you read, some of them use circles or spheres instead of rectangles, but it doesn't really matter, right? Because if you can draw a rectangle around something, that means that you could make a circle that had the same diameter as the diagonal of that rectangle that would contain it, right? So it's really just a point of view. So in reality, any geometric figure that you can contain it in, as long as it's finite, is acceptable. So, all right, let's move on to our next example. So a farm has 80 acres of cropland. The farm wants to plant both corn and soybeans. The farm has 200 hours of labor available. Each acre of corn requires 3 hours of labor, and each acre of soybeans requires 2 hours of labor. Plot the solution to this linear system. The solution is called the feasible region. We'll come back to that part. So we have two inequalities here, and there are a couple of inequalities that are implied that were not included in the original problem. And what I mean by that is it possible for somebody to plant a negative acre of corn? No. What's the least amount of corn anyone can plant? 0, right? That's the same amount of corn I planted last year, which is 0, which is the smallest amount of corn any one person can plant. So we have both then that the corn has to be greater than or equal to 0 and the soybeans has to be greater than or equal to 0. So we need to define some variables. So let's let x be the number of acres of corn, and let's let y be the number of acres of soybeans. we need to write down some inequalities that describe this. So as we just talked about, we know then that x has to be greater than or equal to 0, and y has to be greater than or equal to 0, because we can't plant negative amounts of corn or soybeans. So then what else do we know? Well, how much farmland do we have available? 80 acres, right? So then the number of acres of corn plus the number of acres of soybeans has to be less than or equal to the total amount of cropland that is available, right? So between the two of them, we can't plant more than 80 acres. We have another constraint on our system. That is, it takes 3 hours to plant an acre of corn and 2 hours to plant an acre of soybeans, and the farm has 200 hours of labor available. So then that's going to be 3 times x, so the time to plant corn, plus the time to plant soybeans has to be less than or equal to the amount of labor that they have available, which is 200, right? So we now have a system of 4 inequalities. So the first 2 explain why the graph is only in the first quadrant, right? Because we can't have negative solutions and we can't have for that, so we don't need any negative x's and we don't need any negative y's, so that only gives us this region. So now we need to graph x plus y equals to 80. So this is equivalent to the line, if I minus x to the other side, negative x plus 80, right? So this one is going to have, let's make it red. It has y-intercept 80, so that's here, and it has slope negative 1, so that means it's going to go here, and we're going to do this with our filled in dot. Then if we check, is 0, 0 a solution to that system? Sure, 0 plus 0 is less than 80, so that would be a solution. So we need to get rid of everything that's over here.
Professor?
Yes.
I have a question, a quick question. It's about...
So we have our second equation, and let's go ahead and do our intercept method or something. So let's see. We need to graph this guy. So we minus 3x, we minus 3x, gives us 2y is equal to negative 3x plus 200, divide by 2, divide by 2, divide by 2. And we get y is negative 3 over 2x plus 100. So that means our blue line starts up here at 100, and then we have a slope of negative 3 over 2. So in terms of a fraction, negative 3 over 2 is the same as negative 30 over 20, because they're just fractions. So that means I go down 30, so from 100 to 70 and over 20, down 30, down 3 over 2, down 3 over 2, play connect the dots, and I get something that looks like this. So then I would need to do another test point, and if I test, if I put 0 into the blue one, is 0 plus 0 less than 200? Certainly. So once again, my solution is the part that is below the blue line, right? So when I get my region, it looks like this. This point right here, this time we can just read it off the graph. This is called a corner point. and we can read off its coordinate this time as 40, 40. Usually, we must solve the linear system to find the point of intersection. So what we would solve then is we would write down the linear system of equations, which would be x plus y is equal to 80, and 3x plus 2y equals 200. Well, the easiest way to solve that is to write it as a matrix, and then RREF that matrix. And let's verify that indeed our solution is correct. So second matrix, we go over to edit, and we have a 2 by 3 matrix, so 1, 1, and 80, and 3, 2, and 200. Oops, 3, 2, and 200. There we go. Second quit, second matrix. Over to math, and we choose RREF. On matrix A, and we get the following as our solution, which is the same thing we got by reading it off the graph. In general, we don't want to trust the eyeball metric and just read things off a graph. We're going to need to solve to make sure that we're getting the exact answers, because reading points off a graph is precarious, but we see in this case we do get the same point of intersection, which is 40, 40. All right, so then our feasible region in this example is the part that's below both the blue and the red line. So we notice that we have this region up until x equals 40 is the part that's below the red line. Then the red and the blue line meet, and then the solution set switches to being the part that is below the blue line, right? So this region represents all possible configurations, x and y, that satisfy that system of inequalities, right? So this tells us that if we picked any point in there, it would be less than 80 acres of cropland, and it would also be less than or equal to 200 hours of labor to plant that much corn and soybeans, right? So the point of intersection is 40-40. That point represents planting 40 acres of corn, 40 acres of soybeans, right? 40 acres of corn would require 40 times 3, so 120 hours of labor, and 40 acres of soybeans would be 40 times 2, which is 80 hours of labor. 120 plus 80 gives us the 200 hours of labor, right? So this region, as mentioned up here, is called the feasible region. So then our goal after we find the feasible region in the next section is going to be, well, now which part of the feasible region gives us a maximum or minimum value for some objective? So now, say we had some more information, like how much profit the farmer makes for soybeans and corn, right? You would want to find the number of acres of each that would maximize that profit. All right, so that is where we're headed right